Today, my mind is working so slowly, holy cow. Okay, today we are going to be working on relations. Today we start relations from chapter 9. So I think in chapter 9, we're really going to only focus on two sections. 9.1, which we'll at least start and make good headway on today. And then 9.5, I believe. So this is relations. And this is equivalence relations. So we won't spend too much time in chapter 9, but we'll spend enough. And then after this, chapter 6, combinatorics. And that'll be the end of our semester, which is coming up in like 2 weeks. So, you know, we're pretty much there. Okay. So someone remind me, what is a relation from A to B? For me, it's, yeah, both cool and scary. Mostly cool, though. I very much enjoy teaching this class, but I also have grading, like other grading besides just this class that I'm eager for it to finish. So what's a relation from A to B? Oh, yeah, I can refocus the camera. Is that any better? Yes, a relation is a subset of the Cartesian product. So R is some subset of A cross B. Exactly. By the way, is this focused? Can you see it more clearly? Is anyone else having issues with the quality of the camera? Okay, maybe, okay. I hope that I'm closing everything else that is open on my computer, which wasn't much, but okay. So here we are. A relation is a subset of the Cartesian product. So we already know that functions can be described as special relations, right? Functions can be described as special relations. Can someone remind me what the relation interpretation of a function is? A function from A to B is a relation such that for every element of the domain, there exists a unique element of the codomain such that AB is in R, exactly. So it's for all A in A, there exists a unique B in B such that A comma B is inside the relation. Once you have specified this, then you've specified what we call a function. But of course, relations can be much crazier. So here's a picture of a relation that won't be a function. I don't know, this is A, B, C, D, and this is 1, 2, 3, 4, say. This relation is going to send A to 1 and A to 2 and A to 4, and it's not going to send B anywhere, and it's going to send C to 3, and it's going to send D to 2 and D to 3, right? So this is definitely not a function because B isn't sent anywhere and A and D are both sent to two different things, but this is certainly a relation, right? This defines for us a subset of A cross B. Here are some elements in there. 1 or A comma 1 is inside the relation, but so is A comma 2. And B never appears. I mean, I can list out everything inside this relation. A comma 4 is in there. C comma 3 and D comma 2 as well as D comma 3. here is the relation. This is some subset of the cross product, and that's enough for a relation. So relations have very little structure. Okay, what I'm going to do now is write up a bunch of relations, and we're going to use these relations in our examples to kind of analyze some properties of relations that we want to ask. So these are all going to be relations. First I need to make a definition. Do I? Yes. A relation. So usually we say a relation from A to B is a subset of the cross product A cross B. But we can also have a relation on A. And what this just means is R is a subset of A cross A. So in other words, there's a relation from a set to itself. And then I say a relation on A. It's just a terminology thing. Okay, so I'm going to set up several relations on Z. Relations. Actually, do we want to do Z or R? Let's do R. Relations on R. So R1 is going to be equal to the relation given by all pairs AB such that A is less than or equal to B. Right? To specify a relation, all I need to do is specify a subset of pairs. The second relation is going to be set of all A, B such that A is greater than B. R3 is going to be the set of all A, B such that A is equal to B or A is equal to negative B. R4 is going to be equal to the set of all tuples A, B such that A is equal to B. This is a kind of very narrow relation, right? R5 is going to be the set of all tuples A, B, A, comma, B such that A is equal to B plus 1. And then let's maybe do a couple more. R6, let's have this a relation on Z to be equal to the set of all A comma B such that A divides B. And then I can do one more, R7. I mean, there are a million brackets are turning into integrants. Nice. Yeah, my brackets aren't so good. R7 is going to be AB such that A plus B is less than 3. Okay, so I have a million relations here. And I just want to kind of use these as examples when we start examining certain things. So as a first check, let's find out a couple things. So let's take a look at the pair 1, 1. This is either in R cross R or in Z cross Z. So I can ask, is 1, 1 in any of these relations? So could someone tell me which relations 1, 1 is in? So it is definitely in 1, right? Because A is indeed less than or equal to 1. It's not in 2 because it is not the case that 1 is greater than 1. It is in R3 because it is the case that A is equal to B, which is one of the possibilities. It's also in 4, again, because A is equal to B. It's not in 5 because 1 is not equal to 1 plus 1. It is in 6 because 1 indeed divides 1. And it is in 7 because 1 plus 1 is less than 3. So the one that it isn't in, it's not in R2 and it's not in R5, I believe, are the only ones that are missing. So this is just kind of a warm-up to get us familiar with thinking about relations in these terms. I don't think this is so disastrous, right? People are okay with what we're doing here? Y'all good? Cool. Let's do another one just for practice. Which relations is 3, 4 in? Yeah, this one's going to be in rather few of the relations. It's in 1 because A is indeed less than or equal to B. It's not in 2 because A is not greater than B. It's not in 3 because these aren't either the same or negative. They're not equal. It's not the case that 3 is equal to 4 plus 1. It's not the case that A divides B, 3 divides 4, and it's not the case that these two add. So actually, I think it's not even in 5, it's only in 1, right? Here, we're asking about whether A is equal to B plus 1. But B plus 1 is 5, and A is just 3. So do we agree now that this actually only appears in relation 1? Okay, cool. So we have a little practice and we have a little flexibility. Okay. Great. So these are just some examples of relations that we can kind of start to consider and think about. Let's start talking about some important properties of relations. Okay. So here's the first one. Definition. R, a relation on A, is reflexive if, for all A in A, the tuple A comma A is inside the relation. So in other words, if you think of a relation on a set A as, I mean, it's going to be ironic what I say, but it's a way of relating some elements of a set to each other. And a relation is reflexive if you take some set, say a set of numbers or a set of people, and every number or every person in that set is related to themselves using the relation R. And notice that this isn't just that some A comma A are in the relation. This demands that for every element of A comma A is inside the relation. Any questions here? Just on the definition. We'll do a bunch of examples, but. So let's look back at our list of examples and let's try to think about which of these are reflexive. Is R1 reflexive? Ooh, I should put boxes here. And I should forget about the Z. So here I should put reflexive. So is R1 reflexive? The answer is yes. R1 is reflexive because if I look at the element A comma A, for any A in the real numbers, it is always true that A is less than or equal to A, right? 1 is indeed less than or equal to 1. 2 is less than or equal to 2. Pi is less than or equal to pi. So all of the real numbers are less than or equal to themselves. So all the tuples A comma A live inside this relation 1. So this relation is reflexive. Check. How about relation 2? That's right. Relation 2 is extremely far away from being reflexive in the sense that there does not exist a single real number such that a single real number A such that A comma A is inside relation 2, because it's never the case that a number is bigger than itself, right? 0 greater than 0. Oh, that's not true. 1 is greater than 1. That's also not true. Pi is greater than pi. It'll never work. Nope. R2 is definitely not reflexive. How about R3? Yeah, definitely. A being equal to B means you're allowed to be inside this relation. So A comma A, since like the pair B comma B will always satisfy the condition that the first coordinate is equal to the second coordinate. So R3 is definitely reflexive. And for the same reason, R4 is definitely reflexive. How about R5? A comma B such that A is equal to B plus 1. Right. This is not reflexive. Can someone tell me why this is not reflexive? Zero is one reason, because for 0, 0 to be inside here, that would mean that 0 is equal to 0 plus 1, which is false. So the moment that I can find one tuple of the form A comma A, which is not inside this set, it's not reflexive. So this is not reflexive. How about A dividing B? Yeah, a number always divides itself because I can always write m as being equal to m times 1. So m divides m. Cool. This one's reflexive. Lastly, a plus b is less than 3. Is this reflexive? Right. Why is this not reflexive? I'm singing yes, no, yes, no. Exactly. Reflexive means that it must hold for every single element inside the set A. So any negative number, or actually any number that is less than 1.5, not including 1.5, it won't work. But for every number large enough, like for instance 10 comma 10, in order for this relation to be reflexive, I need 10 comma 10 to be inside the relation, but 10 comma 10 does not satisfy 10 plus 10 being less than 3. So this is not reflexive. Is that okay? So are we feeling a little more comfortable with our notion of what it means for a relation to be reflexive? At the very least, we've seen some interesting examples where relations that are very reasonable, because all these relations are very understandable, and we see that there's a good smattering of some of them which are reflexive and some of them which aren't. Let's have an additional question. Let's say the set A is equal to the set of all people. So what's a relation on A which is reflexive? Yeah, A is equal to B is always going to be reflexive. That's true, but that's kind of a boring one. Let's find something a little more interesting. Right, people are themselves, so that's exactly what Val said. A is equal to B is this person the same as this other person? And so that's going to be reflexive and nothing else fits in there. But for instance, another example of something which is reflexive is like belonging to the same family. A comma B belong to the same family. People who have the same name also works, right? People who have the same name. A, B have the same name. Those are two excellent ones, right? So being your cousin's cousin, what exact relation would you have there? Because it's not the case that you could say A and B are cousins, because I don't count myself as my own cousin. Right, so this one is not reflexive. Being in the same family? Well, being in the same family, I would agree with the statement that I am in the same family as myself. Like, if you're asking, like there's the family Besson, and A and B are related if A and B are both Bessons. So then AA works, for instance. Now, technically, this isn't reflexive because there are many people who are not Bessons, so then B comma B would not be inside the relation A comma B are related if A and B are Bessons. But if I say are both in the same family, then you're always in the same family as yourself, right? So these examples with people are really fun to explore these relations with because they're very concrete, right? Like on one hand, sure, numbers are very concrete and this is fun to play with too, but it's also fun to talk about relations in terms of people. It makes for a very kind of, it's a place where you're very comfortable thinking. So that's good. So are we okay with some of these examples in terms of people which are reflexive and which are not reflexive? Kind of fun, huh? Shall we move on to the next? The next interesting property that a relation can or cannot have or need not have? Or should we do something more with reflexive? I probably will wait until someone tells me one way or the other. Okay, cool. Any questions from anyone else? It's okay, everyone's asleep. Let's continue. So the next one that we want to define, so here's the next definition, is a relation is symmetric if A comma B inside the relation implies B comma A is inside the relation. So basically, for any pair A comma B that lives in there, you check, does the reverse pair automatically live in there? And if that's the case for every pair that its kind of reverse pair lives in there, then the relation is symmetric. So, symmetric. Is the first relation symmetric? Is it the case? Is this what my thesis? No, this is quite a different notion of symmetry. Yeah, this this notion of symmetry is much less structured than what I work with. Right, so R1 is not symmetric because there exists a pair, for instance, 0, 1 inside R1 because A is less than or equal to B, but 1, 0 is not inside R1. So the moment that I find a pair where one element is in the relation, but its reverse is not inside the relation, I know that this relation is not symmetric. Is that okay? Is that clear? How about R2? Also no, for pretty much the exact same reason. I can find actually any pair that lives in here has A greater than B. If I reverse it, then now A will be less than B, so that reversed pair cannot possibly be in R2. So this is not symmetric. How about R3? R3 is symmetric. The only types of things which are in R3 are either things of the form A comma A or A comma negative A, right? But the reverse, so to speak, of A comma A is just A comma A. Well, that's in there. The reverse of A comma negative A is negative A comma A, but this is the same thing as negative A, negative, negative A, right? This is the same format where A is the negative of negative A. So maybe, I wish I had more space. I wish I could erase all this scratch work because this is going to get really messy. But I want to keep these examples up, you know what I mean? Because we're kind of going through this list. So some examples here are like, here's some things inside R3. 2 comma 2 is in there, and also 2 comma negative 2. And my next question is, well, 2 comma negative 2 is in there. In order for this relation to be symmetric, I need negative 2 comma 2 to also be in the relation. But does negative 2 comma 2 satisfy A is equal to negative B? Yeah, it does. Just like 2 comma negative 2 satisfied A is equal to negative B. Both of these pairs belong. So this one is symmetric. Is that okay? How about R4? The only pairs inside R4 are A comma A, but the reverse, so to speak, of A comma A is just A comma A. So we already know that's in there. This one's definitely symmetric. A comma B such that A is equal to B plus 1. Is this symmetric? Definitely no, right? This is pretty clear. Here's a pair that's in here. 1 comma 0 is inside here because indeed 1 is equal to 0 plus 1, but 0 comma 1 is not in here. So this is not symmetric. How about A and B such that A divides B? This one is also not symmetric because it's possible, say, 1 divides 7. So 1 comma 7 is in there, but 7 comma 1 is certainly not in there because 7 doesn't divide 1. So no, this one's not symmetric. How about R7? Oh, I think 7 is symmetric. I'm looking for all tuples A comma B such that A plus B is less than 3. Okay, so let's consider one such pair. Let's say 1 comma negative 5, because 1 plus negative 5 is less than 3. But there's a symmetry with the relationship of addition. So negative 5 plus 1, or negative 5 comma 1 is a different tuple, but when I apply the condition, 1 plus negative 5 is the same as negative 5 plus 1. Their sum is going to be equal. So the relation here only cares about their sum, so it doesn't matter in which the pair comes. So R7 is symmetric. Namely, for any pair A comma B such that A plus B is less than 3, it is also true that B comma A is in the relation because B comma A, well, B plus A is equal to A plus B. So if A plus B satisfies being less than 3, then so does B plus A. So what do you mean by symmetric about the origin? I'm going to say that that in general makes no sense. And so first of all, that makes no sense in the context of relations in general, because there's no good notion of origin, especially if you consider the set of all people, right? Second of all, even if you do think about relations in terms of real numbers or integers, then what do you mean by symmetric about the origin? I definitely think that R7 doesn't look symmetric about the origin. I mean, I don't actually know what that would mean to look symmetric about the origin, but if you tell me something, if you tell me a definition of symmetric about the origin, R7 probably doesn't satisfy it. So here's what you could be thinking. You could interpret a set of pairs as a pair of real numbers, right? So then you have a pair of real numbers is inside, like you could try to sketch out sections of the plane. For instance, A is equal to B is this line. This relation is given by A is equal to B. And similarly, A is equal to B or A is equal to negative B is kind of satisfied by this cross, right? So these things, I can understand an interpretation where every point that satisfies the relation, you fill it in black on the Cartesian plane. And so here, this one looks symmetric about the origin for some definition. This one doesn't. But let's look at A plus B is less than 3. Here, the graph somehow of this relation, A plus B is less than 3, is going to look like, here's the A axis, here's the B axis. It's going to look like this, 3, 3, and then we're going to have a dotted line through here, and everything below that is filled in, right? Because, for instance, 0, 0, those add up to being less than 3. And if I don't go past this line, then the sum won't be greater than 3. So everything below this line and not including this line, oh, you can't see. This is somehow the picture of this relation. So there are kind of a host of things going on here. One is that if your relation is a relation on R, then you can depict it as a subset of the Cartesian plane. That's true. But if your relation is just a relation on the set of all people, then you can't describe that as a subset of the real line in a nice way. And then even if you do describe it as a subset of the plane, then a lot of these relations end up being very far from symmetric, you know what I mean? But it's a very good question because it opens up this whole area of how to think about these things. So I'm very happy with that question. Did my ravings and scrawlings here kind of make sense for this way of how to think about relations, these relations graphically? Okay, but once again, there are a lot of relations that we can't think about graphically. So for instance, let's now go back to A is equal to the set of people. A equals set of people. Oh, that is not how you spell people. So let's find some relations on the set of people which are either symmetric or not symmetric. So let's start with some symmetric ones. And I'll bring one from up above. A and B are cousins. This is symmetric because if A is a cousin of B, then B is also a cousin of A. So this relation, which was not reflexive, is symmetric. What's another symmetric relation on the set of people? Two people knowing each other, or let's say being friends, because, well, I mean, yeah, right. Knowing each other, right. So let me do friends, right? So A comma B, if A is a true friend of B. So if A is a true friend of B, true friendships involve both people being friends. So I would claim that true friendship is a symmetric relation. If A is a true friend of B, then B is a true friend of A, right? Exactly. I mean, right. So this true is trying to explicitly avoid one-way friendships. And I'm also trying to avoid the relationship between celebrities where like I know tons of stuff about. I'm not going to tell you who I know tons of stuff about, but there are people whom I know plenty of things about and they know nothing about me, right? So that in that sense those relations could be not symmetric. You all are free to speculate. So what's a non-symmetric relation on the set of people? Yeah, is younger than. Yeah, that's a perfect one. A and B, A is younger than B. Another one is AB if A is a parent of B. If A is a parent of B, it is not the case that B is a parent of A. Right? So these are some non-symmetric relations on the set of people. Anyone else have a nice one that they thought of? Either symmetric or not symmetric? Here's a good question. Yeah, these are good ones. So A and B work together would be symmetric, and A knows a lot about B is probably not symmetric because that's essentially the celebrity relation. Or not celebrity, but yeah. If A knows a lot about B, that does not mean that B knows a lot about A. These things are clear. Yeah. Let's find some kind of more particular examples. Let's find some relations on the set of people. So let's find a relation R, which is neither reflexive nor symmetric. Reflexive and not symmetric. Symmetric and not reflexive. And both. So what's a relation on a set of people that is neither reflexive nor symmetric? I already have an idea for this one because it's one that we've already said. So I would argue that this is a reflexive relation because A should always know a lot about A. I mean, this depends on where you fall on the kind of mental health and how much someone knows themselves thing. But I would argue that most people know more about themselves than anyone else does. Maybe that's a flawed assumption, but I'm going to make that argument right now that the relation A knows a lot about B is actually reflexive. I would say a relation here is A, B, such that A is a parent of B. First of all, no one's a parent of themselves because time travel is impossible. And second of all, this is the plot of Back to the Future, right? And then if A is a parent of B, then B is not a parent of A. So I would claim that A comma B, where A is a parent of B, is neither reflexive nor symmetric. Well, Oedipus wasn't his own parent, right? Oedipus just just thought he was somebody he wasn't. You can be a step parent of yourself. I'll give you that. Oedipus. Okay. Let's find a relation which is reflexive but not symmetric. And this one we already know as well. here I would say A knows about B. So A, B, such that A knows about B. You know about yourself, but just because you know about someone doesn't mean they know about you. In the words of someone I look up to and respect, what you know about me. Okay, symmetric but not reflexive. What's a symmetric but not reflexive relation? I think this one we also have an example of. Yeah, cousins. A, B, such that A and B are cousins. This is reflexive because if A is a cousin of B, then B is a cousin of A, but A is not a cousin of A. And then both, something that is both symmetric and reflexive. What are some good examples here which are not just the relation A comma B such that A is equal to B? Here's one, as Val suggests with this is A and B respect the same person. Will that work? Yeah. A and B such that A and B respect someone, some person C. So I certainly respect all the people that I respect. And also, if I respect someone that person B respects, then it's also the case that B respects someone that person A respects. So this is cool, right? How many minutes do we have left? What a fun class. Okay, I've got time for introducing the last interesting property that I want to bring up, and this is transitivity. Definition. Transitivity. So a relation R on A is transitive if for all A comma B and, if A comma B and B comma C are both in R, then A comma C is in R. So transitivity is maybe more challenging to check because you have to look at all pairs of tuples or pairs of pairs such that the first term of one is equal to the last term of the other, and then you have to see, can these be kind of conjoined, or actually what we'll see is composed, and does AC live inside the relation? So let's go back to our mathy examples before we get to family examples. R1, is R1 transitive? Yeah, this is transitive. If A is less than or equal to B, and B is less than or equal to C, then it's certainly the case that A is less than or equal to C. This one's transitive. How about R2? If A is greater than B and B is greater than C, is it the case that A is greater than C? Also yes. This one transitive? So this is saying if I have tuples in there, A and B, so what are the possible tuples that I could have? I could have something of the form A comma A and then A comma negative A. I could also have tuples of the form A comma negative A and then negative A comma A. Or I could have a tuple of the form A comma A and then A comma A, right? But in each of these cases, if I have A comma A and A comma negative A, then I'm asking, is A comma negative A inside the relation? Or similarly, if I have A comma negative A and I have negative A comma A, is A comma A in the relation? And if I have A comma A and A comma A, is A comma A inside the relation? So this one's, you have to kind of think about it, but this one does end up being transitive. So we're on 3. So what is the A is equal to B is equal to C one supposed to be for? So for number 3, the only possibilities are that the second coordinate is either the first coordinate or the negative of the first coordinate, right? I'm only considering things that are already inside the relation. You're using too many letters, basically. The only things that appear inside R3 are A comma A or A comma negative A. And what I'm looking for are pairs such that the last term of one and the first term of the next agree. So I think I've specified all the ways that that can happen with these 3. And then I compose them, that is, I delete these 2 and I make A comma A a relation, or for instance, for A, and A negative A, what I'm asking about is A comma negative A, but this is also inside the relation. Does that make sense why R3 is transitive? I'm only looking at tuples of the form A comma A or A comma negative A. A comma B is obviously transitive because the only relations in here are A comma A. So, okay, you're good. A is equal to B plus 1. Is this transitive? Why is this one not transitive, Mahita? Can you give me a counterexample? I can give a counterexample, which I'll do really quick because I'm already over time. 2 comma 1 is inside here because 2 is equal to 1 plus 1. And 1 comma 0 is in here because 1 is equal to 0 plus 1. But once I have 2 comma 1 and 1 comma 0, my question is 2 comma 0 inside the relation? And the answer is no, because 2 is not equal to 0 plus 1. Yeah, so you had the exact example. A is equal to C plus 2, right? So here we have 2 tuples, which are inside the relation, but, so this is AB, this is BC, and then AC is not inside the relation. So this is not transitive. How about A dividing B? If A divides B and B divides C, does A divide C? Yeah, this one's transitive. And the last one is, if A plus B is less than 3 and B plus C is less than 3, does that mean A plus B is less than 3? Or A plus C is less than 3? Yeah, this one's definitely false. A counterexample would be like 3 and negative 1, right? Because 3 plus negative 1 is less than 3. And then I could do negative 1 and 3 because, or let me do negative 1 and 2 because negative 1 plus 2 is less than 3, but 3 comma 2 is not less than 3. So these two are inside R7, but this one is not inside R7. So this is not transitive. I know that this is extremely messy and extremely chaotic, and I apologize, but hopefully y'all can listen to what I say, which is more useful than what appears on the page. Look at that, another day where I went 3 minutes over. Any questions on this? When we start up again on Friday, we'll go back through, like, we'll discuss transitivity on the level of people, we'll discuss composing, and then we'll get into equivalence relations. Definition of transitivity is right here. If A comma B and B comma C are in the relation, then A comma C must be in the relation. Yeah, so this is like deleting the middle, so to speak. You find something A comma B and you find something B comma C and you're like, can I kill the middle and get A comma C? And if you can always do that, then you have a transitive relation. If you have one example where you can't do this, then it's not a transitive relation. All right, that's the end of class. Thanks for joining me today, and now y'all can go off and stress about different stuff. Yeah, have a nice day, everyone.